And so now that we've talked about the gravity force, which is the force experienced by an object uh, that attracts it to the center of gravity of the planet it is sitting near, we can talk about the tension force. So when you have a rope attached to an object, in fact it should be attached to two objects, when you have a rope attached to two objects that are both providing a pull in opposite directions, then that rope will be under tension. And so this tension force will be directed along the wire, so in the direction of the wire, and it'll pull just as the objects pull on the rope also pulls on the objects. So let's say that this object here is providing a force of, say, 10 newtons. It's maybe it's a car or something, toy car on wheels. So we can imagine wheels being on there. And this is also providing a force of 10 newtons, but in the opposite direction. And so this whole system won't be moving, and the tension on the rope then will be the force that is common to both. So there'll be a tension force of 10 newtons. Now, if this toy car was providing a force of 15 newtons this way, and this car was only providing a force of 10 newtons this way, in fact, let's say 5. So we got 15 newtons over here and 5 newtons over here. This whole system would be moving to the left, right? Correct. This whole system would be moving to the left. Why? Because this is providing a greater pull than this can provide in the opposite direction. Now, what's the tension in the rope in that situation? The tension, if this is 15 newtons and this is only 5 newtons, the tension in the rope in that situation is only 5 newtons. Why? Because 5 newtons is the force that is common to both, in both directions. So 5 newtons this way, there's also 5 newtons this way. The other 10 is the net force which pulls this whole system to the left. And so the tension in the rope is equal to the force that's provided at either end in opposite directions. So in this case, 50 newtons to the left, 5 newtons to the right. The tension is only 5 newtons in the rope. Now, from the point of view of the objects, this object experiences a tension force to the right. This object experiences a 5 Newton tension force to the left. And so the tension force is always perceived by the objects the rope is attached to as being towards the center of the rope. And this makes sense because if you think about, say, a tug of war, you're pulling in opposite directions, and your team will experience a pull towards the center of the rope, and the other team also experiences a pull towards the center of the rope. Now, the tension doesn't have to be horizontal. You could have a rope hanging, an object hanging on a rope vertically, and then the tension on the rope is also the gravitational force acting on the object. Why? Because Newton's third law. Because, let's look at this object. There's gravity pulling down on it, and yet if it's not accelerating downwards, there must be a force pulling upward on it as well. That upward force would be the tension on this rope. And again, if it's not accelerating, well, we know that there's no net force acting on the object. If there's no net force, that means that the tension force, Ft, will equal the gravitational force. These two must be equal because in the vertical, this object is not accelerating. So with F net equaling ma, if there's no acceleration, then there must be no net force. All right, so we've talked about the gravitational force, and we've also talked about tension forces that can be present if you have a rope attached to something. The applied force is the third force we'll look at, and the applied force is just any force that that we willfully apply to an object. So if you're pushing a desk across the room, then the applied force is the force you exert on the desk to push it. All right, next up is the spring force, and this one takes a little longer to understand, perhaps, to explain anyway. So, the spring force is the force exerted by a deformed spring upon any object that it is attached to. Now, what that says is the deformation, in this case, refers to either stretch in the spring or compression. So the deformation covers both of these, depending on what kind of spring you're talking about. Now, when an object compresses or stretches a spring, it's acted upon by a force that restores the object to its rest or equilibrium position. So what that means is, let's say we have a spring like this, and an object being pushed upon by some force. We'll call it Fa for applied force. Now, given that this applied force is not infinite, this object will eventually stop, like the spring will stop it from moving. So at that point, the spring is providing, at the point where it's stopped, the spring is also providing a force. Now, the way we calculate the spring force is this way. Before, if you imagine a slinky, you can stretch it to a certain point, and after some certain point, the slinky stretches out permanently and doesn't function very well as a slinky anymore. Before that point, the slinky is deforming elastically. That is to say, it comes back to where it started. So all springs are kind of like that. If you stretch them or compress them too far, they'll deform plastically or permanently. So before that happens, while springs are functioning in their elastic zone, they follow something called Hooke's law, which says that the force that you apply to a spring, and likewise the force that the spring applies back to you, because of Newton's third law, that force is equal to K, which is called the spring coefficient, times X, which is the deformation of the spring, which is the difference in the between the original length and the deformed length. K is the coefficient, the spring coefficient, and the spring coefficient is just a measure of how springy the spring is. If you think about, any spring, a springier spring will have a higher K. That is to say, a spring that's harder to stretch or compress will have a higher K. And so, for a given deformation, a spring with a high K will require a higher force. So, in order to compress one spring by 5 centimeters, the force will be high. If the K was lower, to deform a different spring by the same 5 centimeters, because this K is lower, you'll need less force to do it. All right, so let's take a look at an example. If a 30 Newton force is applied to a pull spring with a spring coefficient of 17 newtons per centimeter, how much does a spring stretch? There's one example. And a spring compresses 3.5 centimeters under a force of 150 newtons. We'll find the spring coefficient. So these are two different examples, 1 and 2. In the first example, we have a force applied to the spring of 30 newtons in whichever direction we happen to be going. This is a pull spring. Let's say that the force is pulling this way. So we have a 30 Newton force. We have a K of 17 newtons per centimeter. There's no direction to K. If we look at our equation, we have F equals K x. In this case, x. We're looking for how far the spring stretches. And so, x is what we're looking for here. We can rearrange for x. So x then equals F over K, which equals 30 newtons divided by 17 newtons per centimeter. And so, in assessing this division, this is taking 30 newtons dividing by 17 newtons per centimeter is the same as taking 30 newtons to the right and multiplying by the reciprocal of centimeters over 17 newtons. This is the reciprocal of 17 newtons per centimeter, 17 newtons per centimeter, but upside down. We end up with units of newtons canceling, and we end up with an answer of 1.76. The units we're left over are centimeters, and the direction is this, to the right, which is to say, in this pull spring, we have, let's see, spring before, spring after, we have an x, or deformation, of 1.76 centimeters. That's the difference between the original length and the final length.